All right, let's get started, everyone. Sorry for the delay. So I have no idea what is going on with this Zoom thing, but it seems to be working, so let's just go with this. I'll try and figure this out for next class. So today we are going to be talking about this high-level task of language modeling, predict the next word. This can be implemented in many different ways, and in this class we will be talking about basically the simplest possible way to do this, which is through an n-gram model. So for this class, the concepts we'll be discussing are quite simple. When we talk about training an n-gram model, we are referring to counting up the occurrences of particular words and then normalizing these counts by a certain value. All right, so before we get started, some impending deadlines. So you have two deadlines on February 16th. One, your homework, the first homework is due. Second, your group assignments, if you want to choose your group members, that is due on February 16th as well. So on Piazza tonight, we will release a Google form link where if you have a team of 4 people or 5 people, you can submit all the names and emails of your team members and we will group you together. And about a month from now, you will have your project proposals due. There will be a template released on Overleaf. So one of the problems in Homework 0 will force you to use LaTeX to do various things like write equations and formatting and so on. You're going to be expected to use that for all of the project deliverables and some of the homeworks as well. And there's a tutorial to brush up on that in case you're not familiar. All right, so clearly the YouTube is working. Hello to you as well. So let's get started with the topic of the class today. Let's say I want to train a model for sentiment analysis. This is an example that we looked at yesterday with the supervised learning paradigm where I would collect, like 50K or 20K labeled input-output pairs, train a model from scratch on this data, and then I have a sentiment model. However, we discussed the advantages of transfer learning. Right? So here I have a pre-trained model that's trained via some sort of self-supervised training objective. So language modeling is one such objective, right? I get labels for this task for free just by collecting as much text as I can and chopping it up into various inputs and output single word, what comes next. So we discussed how when you pre-train a model on a self-supervised task, and you scale up that model such that it gets very good at predicting the next word, then we can kind of specialize this general pre-trained model to the task that we actually care about, in this case, sentiment analysis, and we get much better performance than in this first paradigm. So this was really popularized by things like BERT when they came out, where you were pre-trained this very large language model and then fine-tuned it for specific tasks. But nowadays, we kind of have gotten rid of the second part for at least the average user who is interacting with ChatGPT, right? They're not doing any fine-tuning. They're just telling this language model what to do in natural language as part of its input, and then it predicts the next word, and it's doing great. So there's a bit of nuance there. A language model like ChatGPT is not just trained to predict the next word, but there are also other steps after that, like instruction tuning and RLHF and things like this that kind of try and align the model better with what humans actually want as output from the model. And we will discuss all of those probably like a month or so from now. But a huge component of ChatGPT, nevertheless, is the gigantic pre-trained language model that is just trained to predict the next word. So that's what we're going to be focusing on today, but we're going to be starting way over here. N-gram models have nothing to do with ChatGPT, but they do serve as a good introduction to the task, the basic math that is relevant even for models at the scale of ChatGPT, and how do we evaluate these kinds of models. And a little later in the lecture, I will show you an example of a state-of-the-art N-gram model that does seem to have some relevance for today's giant neural language models as well. Okay, so let's start with an introduction of the task. What is language modeling? We already talked about predicting the next word given some context, but this actually is the same task as assigning a probability to any piece of text, and we will see this a little later on. But a language model allows us to get the probability of any arbitrary piece of text. So you might think, why would I care to do this, right? Why do I want, what does it mean to have a probability of some string? So if you're thinking about, say, machine translation, right, and you have multiple candidate translations and you're trying to pick which one is the most likely translation, and maybe I had two translations. I flew to the movies and I went to the movies. If I had a method that could measure the probability of these two translations just in isolation, and it could tell me that I flew to the movies is a very, very uncommon thing to say, right? It's very, I mean, who's doing this? Maybe some rich billionaires or something. But I went to the movies, way more common, so maybe it's more likely to have as a translation for some given sentence. And it's a little more apparent in speech recognition, right? So if I have some audio file and I have two candidate pieces of text that could be transcribed from that, I saw a van or eyes of an, right? The latter string here doesn't really make sense, and so we might prioritize the former, which is actually grammatically correct English. So a language model allows us to measure the probability of a piece of text, and it also allows us to complete a piece of text with the next word or words that follow. So, you know, Google autocomplete, for instance, or whatever, when you're texting on your phone and you autocomplete something, some word or some sentence, this is relying on language models, right? This is like a very direct application of a language model. What is the weather? What is the meaning of life? These are all things that are highly probable under whatever this language model is. Okay. So more mathematically, let's say we have a sequence of words, a piece of text. We're going to call each word W sub I. So the first word W1, W2, W3, and so on. So our language model is going to be able to compute the probability of this entire sequence, as we see here, P of capital W. And the way it does this is it's going to be estimated to produce these conditional probabilities. So the probability of word 5 given words 1 through 4, right? This is actually what we're going to be estimating in most language models that we see today. However, you could design language models that don't operate by estimating this, but just take into account the probability of strings. So one way you could do this, for example, is take every possible string that you observe, every sequence of n words, and count up how frequently that sequence of n words occurs in some data set, and divide over the total number of sequences of n words. However, you quickly run into problems of sparsity. If n is very large, you might not ever observe any sentences or sequences that have those exact words in that order. And so maybe this is not a good approach to computing or estimating a language model. So as we'll see, there are some tricks to try and get around this sparsity problem and also make this language model that we're eventually estimating a lot better. So a model that computes either of these, the probability of the full piece of text or these conditional probabilities, is called a language model. And you can see how they relate to each other by simple application of the chain rule of probability, right? So we can review this through an example. So let's say that our word 1 through word 5 here is this sequence of 5 words. Its water is so transparent that. So this is part of some larger sentence. And let's say we want to compute the probability of this piece of text, this 5-word sequence. So when we use the chain rule, we can factorize this joint probability of this whole sequence into the product of these conditional probabilities. So you've probably all seen this equation before in various math classes. P, A, B, C, D, this joint probability is equal to the probability of A times the probability of B given A, the probability of C given A, B, and so on, right, for as long of a sequence as you want. And so we can apply this to the problem of language modeling. The probability of a piece of text is just the product of these conditional probabilities of word n given all of the words up to word n minus 1. Does that make sense? It's pretty straightforward. So taking our example from before, the probability of its water is so transparent is equal to the probability of its times the probability of water given its times and so on. So how might we estimate, let's say, the probability of its? Any ideas on how we could get a good sense of what probability of its means? Yeah, exactly. So I can take a huge collection of text and count up how often does every word occur in this piece of text. So how often does the word its occur compared to the total number of words, right? So I guess compute the frequency and that becomes my probability of its. So this, what we just did, is called a unigram model. This means that we are computing the probability of its without any context, like any preceding words, right? And the unigram probability, it's called a unigram, it's just one word, is just the frequency of that word in a given piece of text. So how might we similarly compute this probability, the probability of water given its, using the same method that you described where we're just counting words in a piece of text? What might be the best way to do this? Exactly. So I can first count up all the times that its occurs, and then look at all the times that water follows its, right? And so I can just normalize that count by the total number of times that it's occurred, and I have this probability, right? So these things that we just did are assuming we have access to some giant collection or corpus of text, and we are able to count up the frequency of different words and different phrases in that corpus. And what we're actually doing is forming the maximum likelihood estimate of these various probabilities, right? Because we have a data set and we are looking to estimate these probabilities that maximize the probability of the data that we are given. And so that is essentially how n-gram models work. You can think of doing it for the probability of so given its water is, right? We find all occurrences of its water is, and all occurrences of its water is so, and just do this normalization. So pretty simple introduction to n-gram models. And if we are allowed to compute all of these probabilities here, we can multiply them together and then get the probability of this entire sequence. Now, of course, if we look at this particular probability here, the probability of transparent given that its water is so were the previous 4 words, it might be very difficult to find multiple occurrences of this prefix, right? Its water is so. So let's say that it occurs twice. We're not really going to have a good estimate of the probability of transparent, right? Because we just haven't seen that many occurrences of this prefix before. And this is one of the limitations of this count-based approach that I'm describing right now, right? We just require seeing a lot of occurrences of a prefix in order to have a good estimate of the conditional distribution of the next word. And so broadly, this is one of the problems that when we get to neural language models, we're seeking to address, where we're not taking into account just the fact that these 4 words occurred, but also their semantics, right? Maybe its water is so is similar to its surface is so, or its liquid is so, or its fluid is so, and we can share information from all of those occurrences to make our estimate of the next word better. All right, we have a question here. GPT-4 is also an n-gram model, right? No, GPT-4 is not an n-gram model. It is a neural language model, which is a different class of models that we will start covering next week. And it addresses many of the issues with the n-gram models that we're going to discuss today. All right, so a bit of terminology. We will refer to this context, or the words that occur before the word that we're trying to predict, as a prefix for the rest of this semester, okay? So this is going to be called the prefix, and our goal is to predict the target word here, the word that comes next. So homework 0 will also have you, counting up these prefixes. All right, so I briefly mentioned this method of estimating the probability of a sequence before. If I have the probability of the given its water is so transparent that, I can simply just count and divide by another count, right? The count of the prefix. However, this runs into the problems of sparsity. And so an n-gram model makes a Markov assumption, which means that it will not consider any words in the prefix beyond a particular fixed window size. So in a unigram model, remember we talked about this over here with the probability of its. In a unigram model, we're going to consider absolutely no context. So the prefix is just not there, and you're just counting up the frequency of this word's occurrence in the corpus, irrespective of what comes before. So a bigram model is the next most complex n-gram model. We're calling it a bigram model because now we're considering phrases of 2 words, where one word is the prefix and the other word is the target word. Here, we have to do what you said. We count up all occurrences of the prefix and all occurrences of the 2-word phrase, and we divide the former by the latter. So here, if I have the probability of the given its water is so transparent that, the bigram assumption simplifies this probability to the probability of the given that, the very last word in this context. So we're chopping off all of this. Its water is so transparent, but in return for removing all of this information, we are getting a better estimate because we have more occurrences of that than we do its water is so transparent that, right? So what is one downside of making these kinds of Markov assumptions? Yeah, we lose long-term context. I mean, depending on your definition of long-term, this is not even that long-term, right? We don't know that transparent occurred or water occurred. We have no idea what the subject of this phrase is. We don't know what this adjective is. We are lacking a lot of information to make a prediction of the next word. Right? If I'm just given the probability of the given that, that's going to be very generic, that prefix, compared to this much more specific prefix. And you can think about in the long term, let's say we have a very long book, right? And we're trying to predict the next word. If we apply a Markov assumption like this, we're just not going to be able to include anything from what happened in like chapter 1 or chapter 2 or any sort of information from the long-term context if we're just chopping the prefix at a particular very small number of words. All right, so this was a bigram model, and it kind of predictably increases as you add more words to the prefix. So this here is a trigram model. We're considering 3-word phrases, right? where the previous two words were transparent that, and the current word is the. Yeah. You always are using the last two words because these are the words closest to the target word. So that's an interesting question. What happens if instead we decide, all right, maybe the first two words of this prefix are more predictive than the last two words? The problem with that is that you ignore local, like, syntactic properties, right? So if I know that so transparent that is what came before, then I know that there's a specific type of part of speech that comes next, maybe like an article or, you know, a possessive or something like that that follows. But if we just know it's water and then blank, 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 and then I'm trying to predict the next word, I lose a lot of the grammatical information about that phrase. Yeah, so for now, we are just computing these probabilities by counting how the occurrences in some large piece of text. Other questions? All right, so let's move on. So let's apply this Markov assumption to our, equation from the chain rule that we were using to get the joint probability of the piece of text by using the product of the conditional probabilities. So here is the, the Markov assumption where in these conditional probabilities, we are just going to ignore all of the words in the prefix outside of the specific window of context. And so you're making this assumption where what really should happen is the probability of word sub I should be conditioned on all of the previous words. But instead, we're making it the probability of word sub I is conditioned on the previous k words here. So this is a very restrictive assumption, but it does enable us to at least alleviate some of the sparsity issues that occur if we are using this count and divide approach for estimating these probabilities. All right, so we already talked about the unigram model, but here's an equation for the joint probability as computed by a unigram model. So the probability of this sequence of words, W sub 1 to W sub n, is just a product of the probabilities of each word in isolation, right? Which is just the frequency of that word in the piece of text that you're estimating this model on. So this model is, of course, horrible, right? You cannot use this model to generate meaningful text. It has no knowledge of local syntactic dependencies or any sort of semantic properties of the prefix because the prefix simply does not exist as part of this model. So you can look at this by actually trying to generate sentences from a unigram model. So this is a piece of text generated from a unigram model. You see that it makes no sense. The words are not coherent. They're not linked by any sort of grammar or anything like that. This also begs an interesting question of how do we generate words from a language model, right? So let's say I have a distribution like this, the probability of word I given all of the words before it. How can I use a model that provides me with these distributions to generate new text? Does anyone have any ideas? Okay, so one approach is at every single time step, or every time I want to produce a word, I will just take the highest probability word in this distribution and produce that, right? That's what you suggest. This is actually an algorithm called greedy decoding. So here, we're always trying to produce the word that the model thinks is most likely under the particular prefix. So that's one approach. But it's not always the best approach. In particular, it might reduce the diversity of the text that you're producing. It might make it more likely that you produce like boring, canned responses. Also, there could be some artifacts in this kind of approach. Nevertheless, this is actually the approach that is used in very, very large language models like GPT-4 where greedy decoding is actually a pretty good way of generating this kind of text. However, as one pot dish suggests, we could also sample from the distribution, right? So maybe, let's say, for instance, this is the probability of dog given I walked the, right? So maybe dog is the highest probability completion of the sentence I walked the, but there could also be some probability on pet or cat. Some people walk cats now, I think, or like other, things that could be walked. And so if you wanted to sample from the distribution, you could, instead of always picking the highest probability completion dog, take a sample from the distribution where you sample each word proportional to the probability that it's assigned in this distribution. And so we'll talk about many different decoding algorithms. That's what this process is called, decoding a piece of text, that are either related to greedy search, or there's a variant called beam search. There's sampling, truncated sampling, many types of sampling. And so we'll have a lecture that covers many of these strategies. But yeah, at the core, you can do greedy decoding. You can sample from the distribution. Does that make sense? Yes.
Even if you have, let's say, 50-50 short sentences, long sentences, the long sentences are going to be lower part of your example. Is there a way to correct for that?
Yeah, this is a great question. So with n-gram models, it doesn't really matter because the context window, the prefix window's length is always fixed, right? So regardless of whether I have a long piece of text or a short one, unless it's like very short, I'm always going to have like, chunks of fixed size that I can count up and estimate. However, your question is interesting because in this generative process, how do I know when to stop generating, right? And that is actually a very important question. What tends to happen in both n-gram models and models like ChatGPT is that there is a special token that's called end of sequence that is attached at the end of every document or every piece of text in the training data. And so that's just treated as part of the vocabulary. So I might have a sequence like, I walk the dog, end of sequence. And end of sequence is counted up just like any other token in the vocabulary, which means that the model has some chance of producing end of sequence at every time it's generating a word. So that's how you need the sequences to terminate at some point, right? But yeah, we'll get back to your question about long and short sequences when we get to a different class of models. It's not particularly relevant for n-gram models. Other questions?
You mentioned like the greedy sequences of sequences what is used in the algorithm or not.
Yeah.
How does it still maintain like grammar and other syntactic requirements if it's just consuming?
So the question is, greedy search, greedy decoding might be used in the largest language models that we have today. How does it consider things like, syntactic properties or semantic properties? So remember that the decoding algorithm is just the way that we are choosing which word to generate next. But the most important thing is the distribution itself, right? So if my language model is really bad, then if I gave it I walk the, it might have no idea what the next word is, and it might say like the or and or of or some random word that does not follow any sort of grammatical conventions or doesn't make sense within the context. But and if I was using greedy decoding, I would pick one of those words and it wouldn't make sense, right? However, if my language model was really good at estimating these probabilities, then the highest probability words would all make sense, be syntactically meaningful and semantically relevant in that particular context, right? So I could have dog, cat, animal, pet, whatever. Each of those would be acceptable to produce, right? And so greedy decoding makes sense if you think about the the top scoring words in the probability distribution to all be very, very meaningful and relevant for the context. All right, so let's move on. Yeah, so here's just a more visual explanation of what we were talking about when we mean we sample from the distribution, right? So given this prefix, students opened there, right? I could have a distribution over the entire vocabulary, all the possible words, unique words that I see in the vocabulary, and they all have some probability. Maybe a lot of them are zeros in this current n-gram setup, but maybe the probability of books is pretty high given this prefix, and laptops. And so if I'm using a sampling strategy, I might sample books the majority of the time, and maybe laptops another large percentage of the time, and sample a word like zoo almost never because it has low probability given this prefix. All right, so we have covered how to generate text from a language model, and note that this is just for one word, right? So let's say I produce the word books. Now, in order to generate the next word, I can just concatenate books to my prefix and then get a new distribution and generate the next word. So using this method, I can generate very long pieces of text by simply just updating the prefix and then generating another token. So a language model generates words one token at a time, left to right, just like we write text left to right, one word at a time. All right, so here's a fun example of what happens when you increase the length of the prefix. So we already saw unigram models are really bad. This doesn't make any sense. You have a sentence that just says which. A bigram model, you start to see a little more grammatical structure that we can recognize at least. He is this palpable, hit the King Henry. It doesn't make sense, but at least, you can see he is this. That's a kind of meaningful ordering of parts of speech. Trigram models get a little better. Therefore, the sadness of parting, as they say, 'tis done. Again, it doesn't really make sense, but it is more grammatical than the previous ones. And 4-gram models are getting better and better. So in general, increasing the order of the n-gram model, the length of this prefix, is good. However, if you increase it too much, you run into this issue where you just don't have enough occurrences of the prefix to estimate this distribution well. And so n-gram models are kind of a balance between, like, you want as much context as you can get without running into a problem where you have either 0 occurrences of the prefix or just a very few occurrences of the prefix. So in general, like before the modern era of neural language models, when people still relied heavily on these n-gram models, huge companies like Google for Google search and everyone else who was using n-gram models set their state-of-the-art values of n to no more than 20, and that was over trillion plus words that these models were being estimated on. So we'll see a nice example of this later on in this class, but yeah.
How do we factor in punctuation?
What's that?
How do we factor in punctuation in these models?
Oh, punctuation. That's a good question. So punctuation is generally treated as separate tokens in the vocabulary. So if you have a comma, that is separated from the word that that immediately follows it and treated as its own word, essentially. Yes? Sorry, is your question that increasing the prefix length will... Oh, why do we only predict one word? Okay, that's a great question. So the question is, why are we estimating just the probability of the next word given the prefix instead of the next 2 words or the next 3 words? Does anyone have an idea why this might not be desirable? Exactly. So the more that you increase that, the more you have to keep track of in terms of how, because you already, let's think about the storage costs of such an n-gram model, right? We saw in a unigram model, I just have to keep track of every single word and how often it occurs in the corpus. In a bigram model, I have to consider every single word and then every single word that it could co-occur with, right? So every possible combination of two words. And then in a trigram model, it's the size of the vocabulary cubed, right? And so every time you increase this order of the n-gram model, you have to increase exponentially how many values, counts you need to store. So yeah, in general, the storage complexity of these models is also a critical limiting factor. You have a question?
Yeah, so two questions. So one, sorry, just one clarification. So gram is represents the number of words.
So you can see that a bigram model is a two-word phrase, but the prefix is only one word, and the target word is contributing the other word of the pair. So in a trigram model, the prefix is of length 2. In a four-gram model, the prefix is of length 3, and so on. Yeah.
And then the other thing is, like, how do they measure, like, how much is too much? Like, I think you said.
So the question, how much is too much, we will get to later in this class. We have to have a way of evaluating how good the model is, right? So we'll get to it in a bit. Let me just try and get through some more slides, and then I'll take some more questions. All right, so as we have already discussed, regardless of what the value of n is, if it's not infinite, then we are losing context, regardless of what we're doing, right? We're always going to chop some words out of the prefix with our Markov assumption, even if n is 30, right? That might not be enough to give you a reasonable estimate of a particular, given a context that requires long-term dependencies. So here is a good example. The computer, which I had just put into the machine room on the 5th floor, crashed. So here, I really need to know that computer was in this sentence, right? But any reasonable order of n is just not going to pick up the word computer, which means that, I need to know that computers crash a lot, right? None of these other words is giving me a useful indicator of what the next word could be. So this is a particular syntactic structure where you see the issues of using these kinds of Markov assumptions. Okay, so I think we already talked about how to estimate these probabilities. We simply just count and divide. I will just emphasize again that this is an example of the maximum likelihood estimate. If you have this setup where you're just counting occurrences of words in a corpus, you want to maximize the probability of your data set. So under this setup, the way to do that is simply to count the empirical frequencies of these words and these phrases in the data set that you're given. So the maximum likelihood estimate of a bigram model on, say, the New York Times is probably going to give you a different probability of, say, I walked the dog than, if you estimated that model on Twitter, right? That's because the data is completely different. The probabilities of the next words that you'll see is very different. And so this is a very data-driven approach. You will have a different estimate of these probabilities depending on what data you're using to get these counts. And obviously, people tend to prefer bigger corpora, right? Bigger collections of text to estimate these probabilities, because that's one way you can kind of reduce the effects of sparsity and also get as many types of diverse data sources as you can fit. Okay, so let's just make sure everyone understands with this simple example. So here we have 3 sentences, and similar to what you were asking, we have 2 special tokens here. We have a start of sequence token. This indicates that we're at the beginning of a new sequence, and an end of sequence token. So the start of sequence token, it serves as part of the prefix, right? We are never predicting the start of the sequence token. But some words are just more likely to occur at the start of a sentence than others. All right, so let's go through some of these probabilities of a bigram model that we are estimating on this small data set of 3 sentences. The probability of I given the start of sequence symbol, right? So let's look at the prefix, the start of sequence symbol. There are 3 occurrences of that. Of those 3 occurrences, the word I follows the start of sequence token 2 times. So my probability of this particular phrase is 2 out of 3. So let's do one ourselves. The probability of Sam given the start of sequence symbol. Anyone have an idea? Yeah, great. It's like we're in kindergarten or something. How about the probability of Sam given am? So here I have only 2 occurrences of Sam, and only 2 occurrences of am, and only one of those times does Sam follow the am, so this is 1/2. Similarly, I can compute all of the probabilities of the different pairs of words, and then I have my bigram model. All of the other probabilities you have in this example are set to 0, right? The probability of the end of sequence symbol given the start of sequence symbol is 0 because we observe none of these occurrences here. All right, so this is simple enough. You can do the same sort of exercise for a trigram model or whatever order of n. All it requires is counting occurrences of the prefix and then counting occurrences of the full phrase and doing the normalization. All right, so one thing that is very important to distinguish is, in terms of terminology, is what is a word type versus a word token. So a word type is what we refer to, what we use to refer to any unique word in the vocabulary. So if our vocabulary here is, I don't know how many unique word types are in here. So start of sequence, I am Sam, end of sequence, do not like green eggs and ham. So maybe there's like 10 unique words or something like that in this corpus, which means I have 10 word types in the corpus. However, a token is any occurrence of a word type. So I could have multiple occurrences of the same word type in the corpus. Here I have I. There are 3 different tokens of the word I, but it's just one word type. So basically the type is a unique word in the vocabulary. A token is the occurrence of any word type in the data that we have. Okay. All right. So this is a nice example from our the textbook that was part of your reading for this class, where they trained n-gram model, a bigram model, on this set of restaurant reviews. So the data set looks like this, and you can look at how this bigram table actually looks. So the table is formed by the prefix word and the word that follows. So you can interpret this as how often did the phrase I want appear in the corpus. The previous word is I, the next word is want. This appeared 827 times. How often did the phrase Chinese eat appear was 0 times, right? So just by looking at this, you can see that most of the entries in this table are 0, right? So we observe a lot of 0 counts, and a lot of that is because syntactically those 2 words just didn't make any sense. But some of that is because it just wasn't observed in this corpus, even though the phrase itself is meaningful. So I can take this table and then I can do the normalization by the prefix, right, to obtain the bigram probabilities. And now I can see that the probability of want given I is 33% in this, this subset of the data set. The probability of 2 given want is 66%. And still, we see a lot of these 0 probabilities here. All right, so now if we have this bigram model that we've estimated from these restaurant reviews, we can use it to compute the joint probability of a piece of text. So here, the probability of I want English food is decomposed into the product of these bigram probabilities, right? So probability of I given the start of sequence symbol, want given I, English given want, food given English, blah, blah, blah. And we get a probability of 0.000031. This is a pretty short phrase, right? It's just like 6 tokens long, right? 1, 2, 3, 4, 5, 6. But the probability is already very low under this bigram model. So what happens if I have a 500-word piece of text that I want to estimate this probability for, right? The probabilities will get very, very low, and we might eventually experience some underflow type errors. So one way that we can get around this, which is very common in all types of language models, is to instead deal with the log probabilities instead of the raw probabilities. So let's say we have this sentence, I love, 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 love the movie, and we have a unigram model that's we've estimated on some movie reviews. So the probability of this, the raw probability of this might be 5.9 times 10 to the minus 7th. The log probability here is just minus 14, right? So this is much more reasonable to deal with and interpret, and also for optimization when we get to training machine learning models for this task. All right, so let's take a look, again, switching back to the raw probabilities at, again, the high-level intuition of why language modeling is an important task. So we see even with bigram probabilities that some types of these probabilities are reflective of important concepts like linguistic concepts or world knowledge or things like that. So here, just the fact that these probabilities of want English or want Chinese are non-zero tells me something about the world, right? It tells me that you know, English food perhaps, or Chinese food, these are types of foods that people might actually want. I might also learn something about grammar, right? That want to is a common syntactic construction in this language. Or, yeah, like the probability of spend want is 0, right? That doesn't make sense. So we're learning that that's probably not a grammatical thing to say. And the probability that I is the start of the sentence is high. We know that that's pretty common, right? I is a very common pronoun to start the sentence. So as you increase the order of n and as you get more and more complex language models, you can start to see many more facts being stored inside the language model, right? What if I had the capital of the USA is blank, right? And if the model puts a high probability on the capital, then it has stored world knowledge inside its parameters somehow, right? All right, so here I wanted to show a very recent, actually this was just like a week ago that this paper was published, and scaling n-gram models to 1 trillion tokens and using a clever variant of to dynamically choose the value of n for different contexts. So basically, it always, if the prefix is never observed in the data set, it will back off, so it'll cut off 1 token of the prefix and try again until it finds a prefix that was actually observed in the data set with some frequency, and then it uses that probability. So it's not a fixed value of n, but a more dynamic construction. Yes? So the question is, when we're training or estimating an n-gram model, do we use the raw token itself, or do we apply some processing like stemming to you know, remove suffixes or whatever? In general, you don't do any sort of processing, especially if your data set is large enough. You just use the raw words. But if you have smaller data sets, then things like stemming might actually be helpful. Yeah. All right, so let's take a look first at the figure in this paper, because I think it's kind of interesting. So here we have this prompt. This paper was done by people at the University of Washington, so their example is also about the University of Washington. The prefix here is conducts research at the Paul G. Allen School of Computer Science and Engineering, comma, University of blank. So this is the computer science building at the University of Washington. But if you're using a 5-gram model, you don't actually get the name of the school, right? So you can see that the most likely completions of the 5-gram are California, Illinois, Michigan, Colorado, Southern. Washington is all the way down here with 2% of the probability. They're saying that if they try and maximize the size of the prefix such that they get, a prefix that they have observed verbatim in the data set at least some number of times, they're able to extend their n to 16. And then they actually observe that at the Paul G. Allen School of Computer Science and Engineering, University of, occurred 10 times in this giant data set of 1 trillion tokens. And so they're able to predict with 100% probability that this is the University of Washington. So this is a good example of, like, if you actually have occurrences of a very long string, it might be an example like this where you can exactly predict what word should occur next. They also have a nice demo on this Hugging Face website here, so I wanted to try this out here. We can even just count the number of n-grams that occur in this trillion-word corpus. So let's take a look at the example that I had before. I walk the dog. I'm sure this occurs like, oh, maybe I should capitalize I. All right, so this 4-word phrase occurs almost 5,000 times. And how about I walk the cat? Okay, so 24 people have walked their cat in this data set. But you can see that as I increase the size of this sentence, it's probably not going to work. So if I said, I walked the dog and then I took a nap, that has 0 count in this corpus. So that's a very natural sentence to say, right? Like you could imagine someone saying that to you, but yet in a 1 trillion token data set, it has not been observed once. Although maybe it's because there's a comma here, I don't know. Nope, all right. So we can also look at the probability of a last token in a particular phrase. So I walked the dog. The probability of dog, we saw already there were almost 5,000 occurrences, but there were 104,000 occurrences of I walked the. So we get this probability of 5%, which I guess makes sense because I walk the doesn't necessarily mean you need to have some sort of noun that you're walking. You could have been I walked the trail, or I walked the big dog, or whatever. There's many possible words that you could have here. Anyway, if you're interested in this, you can play around with it. You can also see the next token distributions. So I walk the streets is actually the most probable thing here with 9%. Then dogs, dog, not sure what this is. Oh, okay, I walk the length of the trail or something like that. But I could probably try something much longer. I walked the dog and then I took a... Oh yeah, this doesn't occur in the... So we actually see some of the limitations of these n-gram models here. But if you're interested in this, please take a look at the paper and the demo that are linked on the slides. All right, so for the last 20 minutes here, we're going to talk about how do we evaluate any sort of language model. So not just n-gram models, but anything, even the ChatGPT language model. Like, how do we evaluate how good it is? There are many ways to do this, but the most common one is called perplexity, and we're going to build up to this metric in the rest of this class. But first, we have to cover some of the basics of just like machine learning. How do you split up a data set when you're training a model? You usually have a train set, a dev set, and a test set. And of course, we want to estimate our model's parameters on the training set and then evaluate it on the test set. The goal is the model has never seen the test set before, and so you would hope that it performs not only well on the training set, but also well on data that it's never seen before. Otherwise, it might have overfit to the training set and isn't capable of generalizing or being useful to arbitrary data. All right, so this is kind of machine learning 101. And so in the context of language modeling, this means that we want our language model to give us a high probability of things in the test set, right? These are human written sentences in the test set, so any model of human language should give that text a reasonably high probability. And basically we want, if we have many different language models, we want to choose the language model that gives us the highest probability of our test set. And so this is what we're going to do with all language models. And here's an example. So let's say that bigram table from before, I estimated it from a bunch of New York Times articles. So my training set in this setting is the New York Times. Now I get all of those counts and probabilities, and I want to use that language model and evaluate it on new data. So maybe I'll take articles from the Wall Street Journal, right? These are different than the training data set. Let's see what the language model actually assigns the probability of these Wall Street Journal sentences. So again, we want a language model that not only assigns a high probability to the New York Times articles, which any n-gram model is going to do, right? Because it saw those texts in its training. So obviously it has high probabilities for the training articles. But what about these Wall Street Journal articles? Those are also valid English texts, right? And they should also receive high probability. Just a side note, in your projects, please do not train on your test set. We have taken off lots of points in the past for people who have done this. It doesn't make any sense if you want to evaluate how good your model is, right? You want to evaluate it on new data, not the data that it was trained on. All right, so we have established that our goal is to measure the probability of some new data using our language model, right? And we've also established that a better language model will assign a higher probability of this new text. And that's written down here. So I'll skip some of this intuition, but basically we can actually just use probability of the held out text as an evaluation metric. However, the metric that we actually used is called perplexity, which is just a function of the probability of the held out sentence. So the equation for perplexity is basically just exponentiating the negative log likelihood per token likelihood of the test corpus. And I want to first give you an intuition behind what this actually means, and then show you the equation and give you some questions to think about. So if we're thinking about perplexity, let's assume we're given a prefix. Let's say I walk the, and we want to know how many different paths or different next words does the model think are equally likely given this prefix. So if the model had no idea what comes after I walk the dog, then maybe it assigns roughly equal probability to all of the word types in the vocabulary, which would mean the model is very confused and has a high perplexity. However, if the model is very good, then it actually knows that, all right, dog is likely, or streets is likely. There's only a small number of words that it considers as reasonably likely given this prefix. And so here, the model might assign like equal-ish probability to maybe 5 or 10 words. And so it has a much lower perplexity than the first one. So you can view this as kind of a branching factor. Given any prefix, how many next words does the model think are reasonable given that prefix? That's the basic intuition of perplexity. And we can look at this more mathematically given this synthetic toy setting. So what is the perplexity of a sentence that consists of completely random digits? So there's 10 digits, right? And if we have a model that just produces random digits, the probability of any digit is 1/10, right? So the probability of any sequence is just 1/10 to the n, where n is the number of digits in the sequence. And perplexity, that computation, just exponentiates by -1 over the length of the sequence. So we get 1/10 to the -1, and we get a branching factor of 10, which means that 10 numbers are equally likely given any prefix. Since this is a totally random model, this makes sense, right? So that's just example of a uniform language model. In practice, when we get to neural language models, we use the negative log likelihood as our training signal. So this is our training objective that we are trying to maximize the stuff in this exponent. So you can see that we have the log probability of word I given all the words that precede I. We're summing these log probabilities over the entire sequence, right? Because when we are using logs, we're summing instead of multiplying the raw probabilities. And then we're normalizing by the number of words in the sequence. So we're getting the average token level probability of the next word under the language model. And perplexity just exponentiates this negative log likelihood. So this is a critical equation that we will come back to next week and in subsequent weeks. This is the actual objective that we will be trying to maximize when we're training neural language models. But I wanted to instead give some sort of higher level intuition of this metric of perplexity. So in particular, let's say I had an absolutely perfect language model that without fail would give me a probability of 1 for every single prefix in the test set for the ground truth next word. What would be the perplexity of this model? So like a totally perfect model of the test set. 1, right? There's only one path that this model thinks is likely given any possible prefix. So 1 is the absolute minimum perplexity that I could get if I had like the best possible language model. What is, let's say now I have, a vocabulary of 100,000 word types, and my language model is just, it has no idea about anything. It considers all words as equally likely. So what is the perplexity of this model? Exactly. So this is probably like one of the worst language models you could get, and its perplexity is 100,000. So the perplexity of any like trained language model is going to be between 1 and the vocabulary size, hopefully as close to 1 as possible. And we actually see that in this, we can look at some of the results in this Infinigram paper. They show you the perplexities on, this is a very long paper. Let's see where they have their, all right. So here we see the validation perplexity, so perplexity on their validation set, and perplexity on the test set. And this is with different types of neural language models. But you can see that the perplexities on these different types of data sets are 13, 11, 9, 5. They're getting better and better, but still, they're not 1, right? So these are some of the state-of-the-art n-gram models, the lowest possible perplexities you can see on a data set of 1 trillion tokens. But still, I mean, this takes a lot of compute to even get to. Most language models you might see that you can achieve yourselves, you might get a perplexity of 10 to 30 or something like that. Just to give you some context of what is a reasonable perplexity. Of course, if in theory the optimum perplexity is 1, but practically speaking, this can never happen, right? Even like a human, like what is a perplexity of a human if they were just reading a piece of text, it wouldn't be 1, right? It might be, I don't know, I can't estimate what that was, but it's definitely not going to be 1. All right. So obviously we now know lower perplexity is a better model. And if you compare these numbers to what we just saw, you see how weak these small n-gram models are, right? A unigram model achieves a perplexity of 962 on the Wall Street Journal test set. A trigram model is at 109, meaning it considers 109 words on average as equally likely given any prefix. So it's not really a good model for doing language generation, but we already know that. It only considers the last 2 words when it's deciding what to predict next. All right, so the last thing that I want to talk about today with regard to n-gram models, and we're not going to talk about n-gram models again in this whole semester, but hopefully it was a good introduction to these general concepts. The last thing is this notion of sparsity. So if we take all of Shakespeare's plays and consider that our training corpus, there were almost 30,000 word types in this corpus, meaning Shakespeare used 30,000 unique words. And there's about 900,000 tokens, right? So occurrences of these word types in this corpus. Shakespeare produced 300,000 unique bigrams, so bigram types, 300,000 unique bigrams, but his vocabulary was 30,000. So there are 844 million possible bigrams that he could have produced if you look at that bigram table, right? Obviously, a majority of these are not going to be grammatical or meaningful, but still, 99.96% of this bigram table is just zeros, right? They were never observed in the training. So that gives you a sense of some of the issues with sparsity that you have to consider even with a bigram model. And so n-gram models are not generally implemented exactly the way that I've just described them. There's an additional component called smoothing, which aims to kind of address some of the issues with bigrams that maybe are possible to appear, but Shakespeare just never wrote them down, but they're perfectly grammatically correct and valid. So if we just didn't observe them, then they don't deserve to have a probability of 0. But we don't know what probability to give them because they never appeared in our training set. So let's take a look at this example. In our training set, we had this prefix denied the appear 4 times. And every time we had a different word come after. Denied the allegations, denied the reports, denied the claims, denied the request. So given this, what is the probability of request given the prefix denied the? Right, 1/4. However, what is the probability of offer given denied the? 0, but denied the offer is a very plausible trigram, right? It could appear, hopefully it doesn't happen to any of you, but, well, I guess you would be the one denying the offer, so maybe it would actually be good for you. But let's say in our test set, we actually have this phrase, denied the offer. So if we had, we wanted to measure the probability of our test set, like we had a giant article that contains this phrase, the probability of this is 0. So when we're multiplying all the probabilities, when we decompose that joint probability using the chain rule, the probability of any document containing this phrase is also going to be 0, right? Just because we never observed this before. And we know that's very unfair, right? Because what if the rest of the document we observed some counts for and we had good estimates of? Why should this tank the estimate of this whole document? So the intuition of smoothing is basically we estimate all the probabilities by counting and normalizing as we did before, but then we are going to steal some of the probability mass from every observed phrase in the data set and distribute that stolen mass somehow across all of the 0 count entries in the table. So here we see allegations, reports, claims, request. Actually, in this example, there were 3 occurrences of allegations and 2 of reports. So let's say we steal 0.5 of the count from each of these, and so now we have 2 counts that we've stolen from our observed counts that we can distribute across all the other words in the vocabulary. So we see here that in the resulting plot, we've reduced the counts of these observed words, but we have a very small non-zero number for every other word in the word type in the vocabulary. So now we don't have any 0 probability phrases in our corpus, so we could estimate theoretically that denied the offer is any document that contains denied the offer, we can still get a probability for it that's non-zero. So this is a very primitive way of doing smoothing. You might imagine ways to better distribute this count, maybe not evenly distribute, but rather, what if we know that all of these are plural nouns? Then maybe we should only distribute this count to other plural nouns in the data set and ignore all other types of words, right? So there's many different strategies you could think of to doing smoothing. There was a lot of research on smoothing strategies 10, 20 years ago. Of course, now we've kind of stopped using n-gram models, but it's still an important concept to understand that this was variants of this kind of approach were used in the state-of-the-art language models even like 15 years ago or 10 years ago. All right, so I think that's all I want to say about n-gram models. Does anyone have any questions? Yes?
Are these distributed only to words that do make sense, or distributed to all the words?
Yeah, so the question is this stolen probability mass or the stolen counts distributed only to words that make sense in the prefix, given the prefix? The answer is no, because we don't really know what words make sense in the prefix. They all have 0 count given our training data. Well, you'll still get some probability for the documents that contain the phrase, so that's the main goal. But yeah, it's not very effective in this method, but there are variants that are more intelligent. All right, so let's end here, and we will start talking about neural models next Monday.